Have you ever felt completely swamped by just an endless stream of information, wishing your brain had some sort of, I don't know, magical bookmark or maybe a summary function for everything you read?
Oh, absolutely.
Or maybe for those of you working with AI, you've experienced that really frustrating memory loss when a large language model, an LLM, just forgets what you talked about halfway through a long conversation.
It's a truly universal struggle, isn't it? Whether you're, a human trying to keep up with the news or an AI processing these massive data sets,
Yeah.
the sheer volume of data we encounter daily, the depth of topics we need to grasp, it really does quickly overwhelm our processing capabilities. It's like you said, talking to a goldfish sometimes when your chatbot just loses the thread.
That's a perfect way to put it. And speaking of groundbreaking, today we're taking a deep dive into a really revolutionary new paper published just this month, July 2025. It promises to fundamentally change how LLMs handle these vast amounts of information. It's called MemAgent, Reshaping Long Context LLM with Multi-Conv RL-based Memory Agent. Quite a mouthful, but important.
It is. And what's truly fascinating here is that MemAgent aims to solve what the authors call the long context trilemma. Basically three things: processing infinite length of text, scaling without performance drop, and achieving efficient decoding with linear complexity.
Okay, linear complexity.
Think of it this way. If your text doubles in length, the processing time only doubles instead of, exploding exponentially like it often does now. This paper isn't just a small step forward. It feels like a monumental leap towards LLMs that truly remember.
Okay, let's unpack this for a moment. So the core challenge LLMs face right now is their limited context window. You can imagine it as their short-term working memory, right?
Exactly.
They struggle with entire books, complex multi-step reasoning, or even just keeping a long conversation coherent beyond a certain point. And this limitation, it leads to pretty significant performance drops, frustratingly slow processing, and that fundamental computational bottleneck, the dreaded ON complexity.
Right, the quadratic scaling.
Which means, as you hinted, processing time quadruples if your input length just doubles. It's why really long inputs become impossibly slow and, frankly, expensive.
Precisely.
So in this deep dive, we're going to explore how this new kind of human-inspired approach works, why reinforcement learning, or RL, is absolutely essential for it, and what the really impressive experimental results mean for the future of AI.
Sounds great.
So to really grasp MemAgent's breakthrough, we first need to double down on this long context trilemma. Why has it been so incredibly tough to solve? You mentioned their typical size context window is a big part of it.
It really is. It's like trying to drink from a fire hose with a tiny straw, like you
Yeah.
said, but maybe the straw is also leaky and the fire hose keeps getting bigger.
Yeah, exactly.
Researchers have tried various ways to extend LLM context, but each has hit pretty significant walls. For instance, you have length extrapolation methods. Think rope-E-based embeddings or continued pre-training.
Okay.
These methods try to stretch an LLM's short-term memory, maybe by tweaking how it understands where words are in a sequence, but they quickly hit a wall. They struggle to scale efficiently to truly vast amounts of text.
They just get bogged down.
Yeah, they get bogged down with significant performance degradation and slow processing speeds, largely because their computational demands just skyrocket with longer texts.
Yeah.
They hit that quadratic complexity wall we mentioned.
Right. So trying to make a small brain handle an entire library, it gets exponentially slower, more expensive.
Okay.
And then there's the second set of approaches, sparse attention and linear attention mechanisms. These aim to reduce that quadratic complexity, right? Make processing more efficient.
They do. That's the goal.
Yeah.
But the downside is they typically require training the model completely from scratch, which is a massive undertaking. Huge cost, huge time investment.
Not ideal.
Not at all. And beyond that, they often rely on what the authors call human-defined patterns to decide what information to focus on, which means they might miss crucial, subtle connections that weren't explicitly pre-programmed or obvious. They have blind spots, essentially.
Okay, that makes sense. And the third category, context compression.
Right. Context compression. This includes methods that try to, condense information to fit it within that limited context window, sort of like making summaries on the fly.
But there's always a but.
There's always a but. These often struggle with extrapolation, handling new information or situations they weren't explicitly trained for, and they typically require integrating additional, sometimes clunky, modules, external memory plugins, things like that.
Which can mess things up.
Exactly. It disrupts the LLM's standard generation process and can create compatibility headaches. It's like trying to fit a detailed novel into a tweet. You lose nuance, you struggle to adapt, and you often need these add-ons that kind of break the core LLM's natural flow.
So if we look back at that trinity, we mentioned infinite length, no performance drop, linear complexity. It sounds like these existing methods just can't quite tick all three boxes.
That's the challenge. None of them fully solve the trilemma.
And that's the formidable mountain MemAgent is trying to climb.
Precisely.
Okay, so here's where it gets really interesting, because MemAgent takes inspiration directly from, well, us, from humans. What was the core human intuition the researchers built upon here?
That's a great question, and it's really key to MemAgent's whole design philosophy.
Yeah.
Think about how you handle vast amounts of information. You don't try to memorize every single word on a page.
Definitely not. My brain would explode.
Right. Your brain abstracts main ideas, you make notes of critical details, maybe use shorthand, and you definitely discard redundant or irrelevant information. You selectively focus. And this intuition, it's not new in psychology. It goes all the way back to George A. Miller's foundational work in 1956 about the limits of human short-term memory. It's about smart processing, intelligent filtering, not just brute force memorization.
So it's about intelligence over just raw capacity. Makes sense. How does MemAgent actually translate that human-like selective focus into an LLM workflow then? What does it do?
Building on that anthropocentric intuition, MemAgent's core design uses a very clever workflow. Instead of seeing one giant block of text, it processes information segment by segment. It treats the whole document like a controlled stream of evidence.
Like reading chapter by chapter.
Exactly like reading chapter by chapter, processing and distilling information as you go, not trying to hold the whole book in your head at once.
And crucially, the LLM maintains what they call a dynamically updated fixed-length memory. Now, what's brilliant here, to me anyway, is that this memory isn't some complex external database. It's simply a sequence of ordinary tokens inside the context window of the LLM itself.
Yes. It's leveraging the model's existing capabilities, its own internal language space, in a really innovative way.
Very neat.
And central to its scalability is the overwrite strategy. This is key. After reading a new chunk of text, the model doesn't just add it. It overwrites the previous memory with an updated one.
Overwrite, so it forgets stuff.
It strategically replaces the old summary with a new, refined one that incorporates the latest chunk. This seems almost too simple, maybe even counterintuitive, right?
A little bit, yeah.
Yet it is precisely what enables the system to scale so effectively. Because the memory stays a fixed length, the computational cost for processing each segment remains constant, what the paper calls O1. Compute per chunk.
Ah, okay. Constant cost per chunk.
Right. And since the total input is just processed as a series of these fixed cost chunks, the overall processing time scales directly and linearly with a total input length, ON. That's how it achieves that linear efficiency.
That constant refinement, that intelligent discarding and updating, that seems like the magic trick. But how does the LLM actually do that on a technical level? What are the moving parts inside MemAgent?
Good question. The workflow basically breaks down into two main modules. First, there's the context processing module. This is the part that iterates over the chunks of text, segment by segment, updating that fixed-length memory each time.
Got it. Step by step.
Step by step. Once all the chunks are processed, the stream is exhausted, then the answer generation module takes over. This module uses only the final aggregated memory and the original question or problem statement to produce the final output.
So it relies entirely on that final summary it built up.
Entirely. And what's truly unique, as you touched on, is that MemAgent summaries, its memory, actually reside in token space, meaning these intermediate summaries are literally sequences of words or subword units, just like the input text itself.
Which is different from how some other memory systems work.
Very different. Many use vector embeddings or external databases. This token space memory is brilliant because it makes every step of its thinking transparent and human-readable. You could, in theory, look at the memory after each chunk and see what the model thinks is important. You could even edit it.
Wow, that transparency is huge. So, okay, this whole design, it directly enables the unlimited length processing because it just streams the document, right?
Right, no inherent limit.
It leads to no performance cliff because The RL aspect, which we need to get into, helps the model retain exactly what's needed.
Correct. The learning part is crucial.
And of course, the fixed size memory means linear cost, finally solving that horrible ON bottleneck.
That's the trifecta.
Okay, this all sounds incredibly elegant, but, for our listeners, isn't reinforcement learning often considered really difficult to train? Especially when you have these long chains of decisions like updating memory over and over. How does MemAgent actually pull this off without getting bogged down? Why is RL, the secret sauce, so crucial here?
That's a really sharp observation, and it gets to the heart of why MemAgent needs RL. You're right, RL can be tricky, but it's essential here because the memory tokens it's trying to learn the summary it builds aren't directly observable outputs you can easily compare to a correct answer during training. They're latent.
Meaning hidden internal representations.
Exactly. And perhaps even more importantly, the critical overwrite decision whether to keep specific information, refine it, or discard it when updating the memory is a discrete choice. It's a series of distinct yes or no decisions at each step, rather than a smooth, gradual adjustment.
And standard training methods struggle with that.
Traditional supervised learning, which relies on backpropagation and continuous gradients, just isn't well suited for learning those kinds of hard, sequential, discrete decisions over potentially very long sequences of reading and updating memory. It doesn't know how to assign credit or blame effectively across all those steps.
Okay, so RL steps in as the perfect teacher for these tricky, discrete, long-term decisions. It frames that overwrite decision, what to keep, what to throw away, as an optimization problem. Is that right?
That's exactly it. The agent, which is the LLM in this case, is essentially rewarded for retaining information that will later prove useful for answering the final question and for discarding distractors that would just waste precious tokens in its fixed size memory.
So it learns through trial and error, getting better at making those smart memory choices over time, like a student figuring out how to take effective notes for an exam later.
Precisely. It learns a policy for managing its memory effectively based on delayed rewards.
Okay, so how does that work technically? What kind of RL algorithm are they using?
To achieve this, MemAgent employs an extended RL algorithm called Multi-Conv DAPO. Now, the base for this is an existing algorithm called Group Relative Policy Optimization, or GRPO.
GRPO, got it.
But traditional GRPO isn't quite enough here. Because MemAgent's workflow generates multiple context-independent conversations for a single query. Each memory update step is almost like a mini conversation the model has with itself.
Multiple steps need coordinating.
Right. Multi-Conv DAPO is designed specifically for this. It addresses this by computing an overall outcome reward from the final conversation, the one that actually contains the answer to the query.
Okay, so it looks at the final result.
It looks at the final result, yes, but then it cleverly distributes group-normalized advantages, basically, feedback signals, across all the preceding memory update conversations that led to that final answer.
So it's not just rewarding the last step.
Exactly. Instead of just rewarding the very final action, Multi-Conv DAPO gives feedback, a kind of credit or blame, to every single step of the memory update process that contributed to that outcome. This allows the model to learn the entire strategy of what to keep, what to refine, and what to discard over the whole sequence, not just the last thing it did.
That's a very clever way to handle that long chain of decisions. Ensure it learns the whole strategy. But, okay, with something so abstract as good memory management, how do they actually quantify useful or important information? What specific metrics are they using for those RL rewards?
That's crucial, of course. They use rule-based verifiers tailored to the task. For tasks where questions might have multiple but equivalent ground truth answers, like a standard QA task where different phrasing is okay.
Like, who directed the movie?
Right. For those, the reward is a max function based on exact equivalence. Did the model's answer exactly match any of the acceptable ground truths?
Okay, simple enough.
But for tasks where all ground truth answers are expected, the example they use is, what are all the special magic numbers mentioned in the text? The reward is different. It's a ratio. The number of correctly included answers divided by the total number of ground truths that should have been there.
So it encourages completeness in those cases.
Exactly. These rule-based verifiers provide precise, quantifiable feedback, guiding the RL process and helping the model learn to selectively retain exactly the information vital for generating the correct final answer, whatever the task demands.
Okay, so the theory sounds incredibly promising. The RL mechanism seems well thought out. But what about the proof in the pudding? How did MemAgent actually perform in experiments? Did it live up to the hype?
Well, the evaluation setup was exceptionally rigorous. They really designed it to push the limits of long context understanding. They primarily used multi-hop long text question answering tasks, which require finding and connecting pieces of information scattered across very long documents.
Multi-hop is always tricky.
Very. And they also used the ruler benchmark. Ruler is fantastic for this kind of work. It's specifically designed with synthetic tasks where you can precisely control the context length and the difficulty, making it ideal for testing a model's ability to locate and extract information over incredibly long spans, like finding a needle in a giant haystack.
And the data set itself, how long are we talking?
The QA dataset was synthesized from a well-known benchmark called Hotpot QA, but they scaled it up dramatically. They created varied test set lengths going all the way up to an incredible 3.5 million tokens.
3.5 million tokens, that's huge.
It's massive. Think multiple long novels combined. And what's truly astonishing here, the kicker, is that the base LLMs they used for MemAgent were only trained with an 8K context window.
Only 8K? That's relatively modest by today's standards for research models.
It is, which sets up a perfect test for extrapolation. Can it perform well on something vastly, vastly longer, orders of magnitude longer, than anything it saw during its training?
Okay, so what were the results?
The main findings are frankly remarkable. They demonstrate what the authors call nearly lossless performance extrapolation. MemAgent showed remarkable length extrapolation capabilities with only marginal performance decay, even as the context length soared into the millions.
Marginal decay? Like how marginal?
Get this, they reported less than 5% performance loss at 3.5M QA tasks, having been trained on only 8K context.
Wow. Less than 5% drop-off going from 8K training to 3.5 million tokens.
It's staggering. To put that in perspective, it's like training a model on maybe a long chapter or a short story and then having it understand the intricate plot points across an entire epic fantasy series with almost no degradation.
That's, yeah, astounding.
And on the ruler benchmark, it also achieved 95% plus accuracy in the 512K token tests, which is, again, incredibly strong for such long contexts, especially given the 8K training.
Okay, that really does shift the paradigm. It's not just a small improvement. It feels like a fundamental change in what we thought LLMs could do with a limited training context. How did that stack up against the competition, the baselines?
Oh, the contrast was stark. The baseline models, including some specifically designed for long context using other methods we discussed earlier, they showed distinct failure patterns and rapid performance degradation. Their accuracy often just plummeted, dropping to 0% accuracy at much shorter lengths than MemAgent handled easily, sometimes even shorter than their own theoretical maximum context length. They simply couldn't handle the scale without their performance falling off a cliff.
Right. And they also did an ablation study, didn't they, to isolate the impact of the different components, specifically looking at the RL training versus just having the memory mechanism.
Yes, and this was a critical finding. It really reinforces the absolute necessity of the reinforcement learning component. They tested models that had the MemAgent memory structure, the fixed size memory, the overwrite strategy, but without the specialized RL training. Those models still perform better than the completely vanilla baseline LLMs, which shows the memory architecture itself has some benefit. But crucially, they still experienced an overall decline in performance as the input length increases, a significant decline.
So the memory structure alone isn't enough.
Not nearly enough. This clearly demonstrates that reinforcement learning is essential for teaching models to properly leverage the memory. It's not just about having the memory slots. It's about learning the intelligent policy for using them, what to prioritize, what to filter, what to update, especially over those millions of tokens. RL provides that crucial learning signal.
That makes perfect sense. And how about its ability to generalize? Could it handle tasks it wasn't specifically trained on, those out of distribution or owed tasks?
That's another key validation point. They tested it on a variety of owed tasks, things like needle in a haystack variants, where a tiny piece of critical information is deliberately buried deep within a massive amount of irrelevant text.
Classic challenge.
Exactly. Plus variable tracking across long text, frequent words extraction, and even question answering tasks synthesized from a different data set. Squad.
And the results?
MemAgent showed consistently superior performance across these diverse task types. This is really important because it validates that the memory mechanism, trained with RL, effectively generalizes. It learns a robust memory management skill, rather than just overfitting to the specific format or patterns of the main Hotpot QA-derived training data.
So it's adaptable. That's really promising.
It really speaks to the robustness of the approach.
The paper includes a really cool case study that illustrates exactly how this works in action. It involves a multi-hop question, something like, the director of the romantic comedy Big Stone Gap is based in what New York City?
Ah, yes, the Adriana Trigiani example. It's a great illustration of the dynamic memory in action. What we see happening is MemAgent demonstrating these intelligent, almost preemptive memory behaviors. Well, first, it might encounter a distractor document mentioning New York City, but not the director. The RL policy has taught it to estimate potentially relevant content from query keywords and store it preemptively. So it holds on to New York City as potentially important, even though it's not immediately connected.
Okay, sort of flags it.
Exactly. Then, later, when it encounters the context that actually connects Adriana Trigiani to Big Stone Gap and mentions her base in Greenwich Village, it immediately updates memory upon encountering context that matches the query. It links the pieces together.
And ignores the noise.
Crucially, yes. It remains unaffected by irrelevant information it might encounter in between those key points. It effectively filters out the noise because the RL has taught it to focus on information likely relevant to answering the specific question asked. It's learning these intelligent memory behaviors through the reward signals, not just through architectural tricks or hard-coded rules. It feels remarkably human-like in its process.
That's a fantastic example. Okay, so zooming out again for the everyday user or maybe developers wanting to build applications, what does this all mean for the computational cost? We keep coming back to that ON Bohr complexity really holding things back.
Right, and that's where MemAgent delivers arguably one of its biggest practical wins. The bottom line here is a truly significant breakthrough in computational efficiency. While those baseline models, even many long context ones, are stuck with that limiting ON and computational complexity, getting exponentially slower and more expensive.
Yeah.
MemAgent achieves that breakthrough linear complexity,
Yeah.
ON. This is an absolute game changer for scalability and practical deployment. It makes processing truly massive documents computationally feasible in a way that just wasn't before.
And just to recap, how does it achieve that linear scaling again? How does it avoid that exponential slowdown?
It comes directly from that core design principle, the fixed-length memory combined with the segment-by-segment processing. Because the memory update cost per chunk is constant O1, regardless of how many chunks came before or how long the total document is.
Right, the cost per step doesn't grow.
Exactly. The total processing time just scales directly, linearly, with the number of chunks, which corresponds to the total input length n. It fundamentally changes the scaling behavior, moving us away from that quadratic nightmare towards elegant, predictable linearity.
Okay, so wrapping this up, what does this all mean for you, the listener, the learner? It really sounds like MemAgent genuinely addresses that long context trilemma we started with.
It certainly appears to.
It offers a practical recipe, it seems, for turning basically any moderately context-sized LLM like the 8K models they used into an efficient, super long context reasoner, something capable of handling millions of tokens. And importantly, it does this without needing exotic new attention kernels or completely altering the standard way these models generate text. It feels like a modular, elegant solution.
I agree. And for you, the potential impact is huge. This could mean LLMs that can finally truly digest entire books, handle complex legal documents from end to end, or maintain incredibly nuanced long-term conversations without losing coherence or forgetting key details from hours or even days ago.
Yeah, imagine an AI assistant that actually remembers your preferences from years of interactions.
Or a medical AI, like you hinted, that can instantly cross-reference every relevant detail from a patient's entire medical history, spanning decades of records, to spot patterns or potential issues. It's about getting more intelligent, more reliable information and insights from AI much faster, and making these powerful models accessible for even the most demanding, information-intensive tasks.
It really opens up possibilities. So here's a final provocative thought to leave you with. Imagine an LLM that could remember everything it has ever read or every interaction it has ever had, potentially for an infinite amount of time. If MemAgent is laying the groundwork for that kind of capability, what new frontiers in knowledge discovery, complex reasoning, and maybe even personalized assistance become possible when LLMs truly have infinite or near infinite reliable memory?